So this is the Senior Math Challenge from 2019. This is, I thought, quite a hard paper. The stuff towards the end is particularly rough, so I'm going to try and get through the first bits as quickly as I can. Don't be a pleb and just work out the actual stuff here. This is what you do year 9 maths for. A squared minus b squared is this. Just put in 1, 2, 3 as a and 23 as b, and you see that this ends up being quite nice, and the answer is this, because you times this by 100, which means adding zeros to the end. Very complicated. Do not do the actual maths. You look like an idiot when anyone marks your paper. Question number 2. I'm going to go back on what I just said. I'm going to do some maths here. 10 minus 9 is 1. 9 minus that is that. I'm just going to do it step by step. That's going to make 1,999. That's going to make where you add there to make this. Then I do some taking away. I mean, my year 7s could do this, right? And the 2 negatives make a positive. Just do it very slowly and gently. Easy. Okay, here, so 1 mil is equal to 1,000 of an inch. Just write that down. And then an inch is 2.5 centimeters. Write that down. And now notice how the answer is in millimeters, which I haven't been given here, so I need to change that to millimeters, which means divided by 10. Sorry, which means timesing by 10. And then 1,000th of an inch is like 1,000th of 1 inch, and now I can put the 1 inch in there and put the 25 there. I know that 25 goes into 104 times, which means it must go into that 40 times, so it's 1 over 40 millimeters. Question 4. Okay, so a prime number is a number that can only be factored into 1 times itself, like 7 can only be written as 1 times 7. Now this can be factored immediately into n times n plus 2. So it's tempting to say that it's never prime, but of course if n is 1, then it's 1 times 3, which means that's prime. So for one value, n is 1, this is prime. For all others, it's something times something else that's not 1, and therefore, because you could try and make that bracket 1, but it would mean making n minus 3, and n is a positive integer, so it's just the 1. Okay, well this one, how many different colors do I need to color this? Well, to start with a blue there, you need to, I'm going to use blue to start with at least. Only one circle is allowed to be blue now, so I can make that one blue, but then this one has to be red, and so does this one. Which I didn't put in, but I said this one could be red because that's this one's kind of red friend, which means that has to be blue. Oh, and then I said this has to be red. Okay, I don't know what I'm doing here, but essentially this is a completed drawing with only 2 colors, in which every color is connected to one color of its own color, and therefore the answer is 2 because I just did it there. Not sure what my logic was, I can't remember. But anyway, question number 6. So this is a grid whereby every row and column and stuff and diagonal multiplies to make the same thing. Now I've got one completed row, which means that each row must multiply to make 50x. I'm also only allowed to use the factors of 100, which are all of these, and I'm going to cross the ones out that I've already used, which is 1, 2, and 50. X just represents one of the factors that I don't know yet, so I'll just leave that. But like I said, each row multiplies the same thing, which is 50x. Which means this column must multiply to 50x, which makes that 25, because 25 times 2 times x is 50x, and now I've used the 25. This diagonal must multiply to make 50x, which makes this x over 2, because 2 times 50 is 100, divided by 2 is 50. So x has to be a number that I can divide by 2, so it can't be 100, because I can divide by that by 2, but it's 50, and 50 is right in the grid, so it's either 20 or 10. Because 5 doesn't divide by 2, and neither does 4, in a way that is a number I still have. But anyway, I can just find out by completely going more on this. This row must multiply 50x, which makes that 4. This must multiply 50x, which makes that x over 4. I've used the 4, so I'll cancel it out. This one must multiply to make that 100, so because that makes 100 over 2x, which is 50x. Cross out the 100, and the only ones left is 5, 10, and 20. But like I said, this one must be x over 4. When we multiply either this one or this one, which means x must be something that can be halved and then halved again, which means it must be 20. Okay, cool. Number 6. So we've got 4 numbers, 1, 2, 3, 4, to make this as small as possible. Well, clearly the biggest numbers need to be on the bottom, 3 and 4. Otherwise, if you put a 3 or a 4 on the top, then you have to put a 1 or a 2 on the bottom, and that makes a fraction bigger than 1, which you know is going to be, it's just not worth trying. You've got to have the biggest numbers on the bottom. Now there is a question as to which way round you put the other 2, so I've got time, I'm just going to try them both. That one makes 5/6, that one makes 3/4, but of course the 11 over 12 and 10 over 12 tells me which one is bigger, and so the 5/6 is the smallest one I can get, I think. Good. Question number 8. So it's asking me for a range of values of x. Well, if I try x as 1, I get 3 to the 3 to the 1, which is 3 to the 3, because obviously that's just 3, which is 27. So that's too small. So now I'll try x as 2, and you get 3 to the 3 to the 2. Why have I put a 3 here? Sorry, that should be a 2, which makes 3 to the 9. Apologies, that number should be a 2. But 3 to the 9 is 3 to the 3 times 3. I mean, I'm just adding the indices here, which is 27 times 27 times 27, which is too big. Right, that's much bigger than that. I can't be able to work it out what it is, but it's bigger than that. So x is 1 is too small, but x is 2 is too big, and so the answer is between 1 and 2 somewhere to make this. Good. Question number 9. So, yeah, you're folding a paper in half 4 times. Now, if you fold this one in half, like along its length and then along its width, you would make this, but you're only folding that in half twice, right? And then when you start folding it again, the little bit here is going to start going everywhere. So it can't be A. Now when you fold in half 4 times, you do this, then you do it again to make like it into eighths. So when we look at this one here and you put it into eighths, you notice every little piece looks exactly like this, right? Like every little piece has a little bit of the circle left over, and so the answer is D. Can't really give you any more explanation as to how I worked that out, but I just kind of looked at it and was like, well, I need to make this into eighths because it's halved 4 times. This is the one that actually looks, every little bit looks like the right place. So you can try it with the other ones, but yeah, it's just going to be D. Number 10. If you do TMUA papers, you'll be used to this kind of question. It's a counterexample question, so for a positive integer n, it wants at least one of 6n minus 1 and 6n plus 1 to be prime, and apparently one of these things doesn't follow that rule. It's asking me which one. So let's write down what each of these two things are for each. So 6 times 10 minus 1 is 59, 6 times 10 minus plus 1 is 61. Do that for all of these. It's not that hard to do. And we're looking for, we're allowed to have one of, so clearly some of these are not prime, right? That's 11 times 11. That's clearly got a 5 on the end, so it's not prime. But it says at least one is prime, so it just wants one of them to be prime. So my counterexample needs neither of them to be prime. Now, I think at least, I'm not very good knowing my prime numbers, but I'm pretty sure at least one of those is prime, because they're low enough for me to not recognize them from the times table. So I'm pretty sure A isn't a counterexample, because I'm pretty certain that at least one of those is prime, if not both. Now, I know that's not prime, and I sort of think this is. So I mean, the answer is not A. I'm pretty sure that is prime. I mean, you can divide it by some random stuff, like 7 and 11 and 13, just to check. But yeah, that seems like it's probably prime, and just do some bus stop division to check. Now that's 11 times 11, and if you do a bus stop here, you see that eventually, if you divide it by 7, you get 7 times 17, so neither of these are prime, which means that's the counterexample, because neither numbers next to it are prime. You can learn divisibility rules, but the only one that I know is adding up the digits to make a multiple of 3 means it's divisible by 3, and the same thing for 9. The others, I think it's just easier to just very quickly get our bus stop and see if you get a decimal or not. I think that's a much faster divisibility test than any actual divisibility tests. But anyway, question number 11. Okay, we want this to be an integer. Now, for this to be an integer, we clearly need k to be a square number, because if you try it without, you get a nested root, a root inside of a root, and that's, I mean, it's just not an integer. It never will be. So we need k to be square. So let's make a table and just put in all the square numbers. So 0 is a square number. And then we work out what 200 minus root k is. And we want this to be a square number as well, so that when we root it, we get an integer. Now 200 isn't a square number. When I root it, I get like something not integered. So that doesn't work. 199 doesn't work, nor does 198, nor does 197. 196 does. It's 14 squared. But you can see as I work down this list of squares, all I'm doing is decreasing by 1 each time. So all I'm actually asking, like all this question actually is how many squares are there under 200? Right? Like how many square numbers are there under 200? And now there are 14, because 14 squared is 196, except we call this the 14th square number, but 0 squared is 0. And we don't count this for some reason, but that gives us 15 squares underneath 200. Because we have to count 0, squared being 0. And that would be what happens if you use 200 squared, which then you root, and then 200 minus 200 gives you 0 here. So it is 15 in total. Okay, number 12. Yeah, this question was hard for number 12. I was surprised. We got a circle radius 1, so the radius goes in this direction as well. And it also goes straight upwards, which is going to be helpful, because my aim here is to work out the area of the rhombus. I'm going to do base times height, and I know the height is 2. So I'm just looking for this base now. Now if I split this kind of shape up into 2, with 30 degrees here and 30 degrees there, I've got a very nice right-angled triangle here, and I can work out this length by doing tan 30 as 1 over x. Now I should know tan 30 is 1 over root 3, which makes x root 3 just by literally looking at it. So x is root 3. And now I need this little length. So again, draw another triangle going out to the corner. This angle up here, well, sorry, this is 60, so this is 60, so this is 120, because they add to make 120, 360 minus 120 is 240, and then divided by 2 is 120. So this is 120, which makes that 60. And again, you can do another triangle here to work out this length, because if this angle is 60, you've got tan 60 is 1 over that little length, opposite over adjacent. Tan 60 is root 3, which means y is 1 over root 3. And so this entire base is root 3 plus 1 over root 3. And the area is going to be that times by the height, which I said already was 2. You can add those together by saying this is 3 over root 3, and then that's 4 over root 3. Times by 2 is 8 over root 3, which you can rationalize if you want to, for 8 root 3 over 3. Thought that was tough for number 12. You need to know exact values. You need to be quite clever with how you split up this shape. I thought it was a tough question, but then lots of questions in this paper were quite tough. This one wasn't. Okay, so he has a square side and he has 64 tiles left over, so that means the number of tiles that he has, which we'll just call x, is 64 bigger than n squared, because he has 64 left over. So x equals n squared plus 64. He has 25 too few for n plus 1, so that means that x equals n plus 1 squared minus 25. He has 25 too few. If he had another 25, it would equal exactly this. Well, okay, we can just set this equal to that, expand out, cancel the n squareds, put the numbers together, divide by 2. If n is 44, you put that into here. You have to square 44, which is a bit annoying, but you do get it eventually. And you add it together for a very nice, lovely round 2000, and you have your answer. Question 14. Okay, so maybe we need to change our perspective here on exactly what a factor is. 15 is a factor of 60, not because 60 divided by 15 is a whole number. I mean, that is a reason. But if you were to write 60 as its prime factorization, which is this, and then 15 in the same way, what happens is when you divide those things, these entirely cancel with the denominator. Like, there's enough stuff in the numerator to just get rid of the denominator. That's what you want for something to be a factor, and that's what gives you a whole number, right? Like, you've got no division left to do. Whereas 14 isn't a factor of 80, because if you write out 80 and then you write out 14, and then you try and divide them, you end up with this annoying 7 that gets left over, which means this isn't going to be an integer, which is what goes back to your definition of a factor, whereby 14 times not a whole number is 80, because of this annoying divide by 7. So I'm just kind of reframing it slightly, because it's going to help here. 10 factorial is what we're dealing with. So if I write 10 factorial as what it is, which is 10 times all the numbers below it, to 1, and then split them up into their primes. So 10 is 2 times 5, 3 is 3 squared, 8 is 2 cubed, and so on. So splitting them all into their primes, and then I'll collect all the primes together under 2, 3, 5, and 7, and I get this because there's 1, 2, 3, 4, 5, 6, 7, 8 2s, and do the same for 3s, just count them up. And what I want is I want to divide them by each of these things, and I want to cancel out everything that I divide by, right? So I want to do 10 factorial over divided by these things, and cancel everything out and not leave anything behind, like here, when it got left a 7 behind. Now, when I do this, I notice that this isn't going to work here, because when you do 7 factorial, regardless of what the other primes do, when you square it, you end up with 2 7s, and I only have 1 7 on the top. So I'm going to have, if I did this divided by this, I would have a spare 7 on the bottom, so it can't be that. Likewise for this one, if I did 8 factorial, so just ignoring the first 2 terms, how many 2s will I have? Well, I'll have all of them except this, right? Because this doesn't contribute a 2, but this does. So 8 factorial only has 1 less 2 than 10 factorial. But then when I square it, so it will have 7 2s, right? Because it only has 1 less. When I square it, it will suddenly have 14 2s. Because it had 7 squares, that doubles the number of 2s. So I'll have 14 of them. And that's way too many 2s. When I do this divided by that, that's way too many 2s. So this is going to have stuff left over. 6 factorial, if I just break that out, that's just this bit. That's going to be what we can see just from the rest of this is 1, 2, 3, 4 2s, 1, 2 3s, and then a 5. And if I do 10 if I square that, so I need to square that, so I just essentially need to double the number of primes I have everywhere. Well, we notice 10 factorial over this, everything lovely cancels except for that 7, which is good, because it doesn't matter if there's stuff left on the top, it's stuff on the bottom. So this is a factor of this, because if I times it by 7, I would get that. So this is the biggest number that works. Again, another tough question. I thought this entire paper was fairly tough. So the highest common factor of all the pairs of these things are 3 different primes. Okay, so again, I can't really explain how I knew to do this so quickly, but if Q is just 2 times 3, if it's just 6, it's just 2 times 3, R needs to share one of these primes. So it can be something like 2 times 5, because that way the highest common factor here is 2, because literally these are the factors, it has 2 in common, so the highest common factor between these two is 2. Now I need a different prime to be the highest common factor of Q and S. Now Q has a 3 in it, so I'll put a 3 in S, and I'll also put a 5 in S because I need to do the same thing with P. So if we look at this, Q and P have a common factor of 2, Q and S of 3, and P and S of 5. And I've made the primes as small as possible because the question is asking me about small things. This is 6, this is 10, this is 15. Add them together and it is one of the answers, which is good, so I think I'm happy with that. If I try and go any lower and just like use 1, 2, then I don't have a second prime to have a different highest common factor with this, and I can't have my highest common factor be 1 because 1 isn't prime, and apparently they're all different primes. So I'm pretty happy that this is the lowest thing I can do. Okay, so again, I had awareness of this problem that maybe a lot of students in year 12 and 13 don't, but if you have 2 equations with 3 unknowns, this is not a solvable system of equations. If you want to solve a system of equations, you need to have at least as many equations as you do unknowns. So GCSE simultaneous equations have an x and a y for 2 equations. 2 equations, 2 unknowns, you can solve it. But if you have 3 equations and 3 unknowns and 2 equations, you can't solve this. There's always this degree of there's always this extra degree that means you can just have a system of solutions of loads of different x, y, and z values. But I'm going to take advantage of that because I'm being told apparently the mean is a constant. Like no matter what the solution is, or the many different solutions, the mean of the x, y, and z values is always apparently the same. So what I'm going to do is I'm just going to choose x to be 0, because why the hell not, and leave my equations to be this and this. And now I know I can solve this. I'll get an x and a y, and then all I'll have to do, sorry, a z and a y, and then all I'll have to do is average this x value with the z and y values that I find, and then I'll have my answer, apparently. So yeah, let's just solve this. I'm sure you know how to do similar equations. The answers aren't too nice, but if you're good with fractions, you can get through it. And then you just add them up and divide by 3, because there's 3 of them. So 0, this, and this. Those add up nicely. Ends up being very nice, and the answer is 10. So yeah, if you're ever given sort of 3-dimensional equations, you can just, but only 2 of the equations, you can just kind of choose one value to be whatever you want, and then solve the other 2. If you ever see that again. This question. Yeah, so this is a lovely question, and it's the kind of question that justifies the fact that you should be looking at all the questions before the end of the time on your paper, because this question is super quick as long as you understand what it's talking about. You have 2019 numbers adding together, and the sum of that is apparently 2019. Now just think for a second. If you start at 1 and add up the first 2019 integers, the sum is going to be much bigger than that. Like much bigger, obviously. Which means to get this sum, you must have to shift back your consecutive integers into the negatives. You must have to add a bunch of negatives to a bunch of positives, which all kind of cancel, and then the last few positive numbers will add up to make that. But of course, if you're doing that, adding a bunch of negatives to a bunch of positives, your list is going to pass through 0. And so when you multiply that entire list together, the answer will just be 0, because it has a 0 in it. So yeah, that's the answer. Question 18. Again, another tough question. This paper was pretty tough. This angle is 90 because it's what was in this corner, which I'll show in a second, which makes that angle 90 minus alpha. So if I were to put this corner back, this angle must be 90 minus alpha, this angle must be alpha, and this angle must be 90, right? Because this triangle has essentially just been folded over to make this one. So I've got two congruent triangles here, they're the same. Okay, what else do I have? Well, I have that the side of the shape is 1. I don't, but I'm just making that up. Let's pretend the side of the shape is 1, which means this side is a half. And it also means this side is 1, because remember, that side is just this side. Now this angle is 90 minus these two, which ends up being that. And this length is a half. And this angle is obviously 90, because this dotted line represents half the paper. So this length is a half. And now, again, I don't know whether there's an easier way to do this, but I have a right angle triangle and I have two of the lengths. So that means that this is the adjacent side, this is the hypotenuse to this angle. That means that cos of this angle is adjacent over hypotenuse. Now, of course, anything divided by 1 is just itself. So cos of this angle here is just this. I'm not sure why I wrote cos in capitals. What a muppet. Anyway, I know that cos inverse of a half is 60. And now, of course, I can just solve this, add 90 to both sides and divide by 2. I don't know whether there's an easier way to do that. I don't think there is. You have to be brave enough to take cos of a weird sort of expression here, but just know that you can do this, and of course you need to know your exact values, otherwise you'd have been stuck. But anyway, that's question 18. Question 19. As soon as I see a question that asks me to match a graph to an equation, I test some values. So if y is 0, firstly, does this graph go through the origin? Like if y is 0, is x 0? Well, if y is 0, you get 0. If x is 0, you get 0. And sine of 0 is 0, so it does. So this graph does go through the origin. So it's not D. And it feels like, you might be like, oh, you've only taken out one graph there. There's still 4 of them. But actually, it turns out that taking out that graph is really helpful. Because what do I notice about this graph that's different to the others? Well, this graph has gaps. Essentially, there are values of x that I could input to this that don't give me any values of y back. Like pretend this here was 5. Apparently if I input 5, I don't get any y values. Now, how could that be the case? Well, because if this side here was negative, and I was doing something like y squared equals -1, I wouldn't get any y values, because I can't square something to get -1. So the question is this ever negative? Because if it is, I'm going to have gaps. So is sine of x squared negative? Well, here's the regular sine graph, and sine is definitely negative. Like sine of 270 is -1 from the graph. But that of course means that sine of roughly 16 squared is -1. 16 squared is, I think is about 256. So if I were to take a value of x of 16, I would get a negative here, which means I won't get any y value, which means this graph does have gaps, and because I eliminated the only other graph to have gaps by saying the graph had to go through the origin, I know the answer is A. Cool, question 20. Let's fill in all the information super carefully. So 2 semicircles. The point O is the center of one of them. The semicircles are equal, which means let's just say, oh, it's an equilateral triangle, sorry, ABC. So 60, 60, 60. Semicircles are equal, so if that distance is 1, so is this distance, because O is the center of one of them, so that distance is 1, and so is that distance is also 1. And of course, so is this distance, because that's a radius. So all of these distances are 1. If I'm just saying that the length is 1, I can make that up. X to Z and X to Y are equal, I think it says. Yeah, are equal, which means this is an isosceles triangle. And I'm being asked for ZXY, so I'm being asked for this angle up here. Okay, well, let's make some progress then. So this length is 1, based on what I said before, which means that this triangle, this little one up here, is actually isosceles, right? Length 1, which makes that angle x, which makes this angle 180 minus 2x, which makes this angle 180 minus 2x. Now this is an isosceles triangle with an angle of x right in the corner, which makes this 180 minus x divided by 2, and also makes this one, and makes this angle here 180 minus this. Well, that's 90 minus x over 2, so this makes 90 plus x over 2. And now let's look at this quadrilateral down here. I know the angles must add up to 360, so I know 60 plus this must equal 360, and when you sort all of that out, you end up with x is 20. And so that would be the answer. Question 21. So we have a square side length 10. From Q, someone sets off at 30 centimeters per minute, which I'm going to say, awkwardly, is 0.3 meters per minute. And the reason I'm saying that is because the answer is in meters. So I've decided to change this to meters rather than centimeters, just making the units the same. The other thing sets up from R and goes at 0.4 meters per minute. And apparently what I'm looking for here is the shortest distance between the two things. Now I'm assuming that they don't just go all the way around, because if they did, because this one's going faster, it would eventually catch up. So I'm assuming that like we're measuring this until this one reaches the end of here, and then the game just ends. Now of course to start with they're 10 meters apart, but as this one goes down and this one goes across, the distance is going to be some diagonal which is going to be less than 10. So I mean the answer isn't 10, I can say that. Anyway, speed equals distance over time. I want some distances, so if I call the time t, this is the speed, which means the distance will be just this times time, so that would be 0.3 t, that would be the distance as t varies. And likewise here, the distance will be 0.4 t. Now this distance then, just from the corner up to the point where this thing has got to, is 10 minus the distance it's gone, so that's this distance here. And I'm looking for kind of this diagonal. And I'm looking for that to be the shortest it can be. Now of course I can set up an expression here, x squared equals this squared plus this squared. I can sort that out and I get this. And now I think this is really tough, but what you need to say is you want x to be the shortest distance possible. So you want to minimize this thing here. Now this is a quadratic, I know how to minimize a quadratic. If you've done differentiation you can do that. If you haven't, you might just be left with completing the square, which is what I did. So I took out a 0.25 first, which essentially just means timesing these things by 4, because then when I multiply through by that, I would divide by 4. And then I completed the square here. So I halved the 24, took away the square of it, sorted that together, and then put the 0.25 through it again, so divided these things by 4 again. And so now I know the minimum happens when t is 12, because that makes this entire thing go away. So the minimum happens when t is 12, and it makes x squared equal to, that should be a plus, and that should be a plus. Apologies, plus plus, it makes x squared equal to plus 64, which means x is equal to 8. So the minimum happens when x is 8. Yeah, apologies there, that should be a plus, that should be a plus, and then it makes sense. I thought that was an unreasonably hard question. I've said that a few times. This paper was tough, man. This question was nice though. I mentioned this in the 2020 paper actually, but functions is a thing that's not covered very well in GCSE or at A level. So I think people have problems with these questions, even though they're really not that bad. I'm trying to work out f of 2019, so it would make sense to put n is 2019 into here, so that I can get an f of 2019 out. So let's put n is 2019, then that gets that essentially makes this. You can see I've just put n is 2019 into all of these things. Unfortunately, this doesn't work out very well, because that makes a 0 of f of 2019, and this makes an f of 0. So I end up working out that f of 0 is minus 2019, which isn't really what I wanted to work out. I wanted to work out f of 2019, but it gives me an idea, which is that, okay, well doing this got me something that I didn't want. Let's do it the other way. Let's work out what f of 0 is. Because if 2019 got me 0, maybe 0 gets me 2019. Put n is 0 in. And yeah, actually, this is good, right? Because then I get this, but I know f of 0 now. So I can put that in. Those multiply to make a positive. And now I can just rearrange for that. And I get f of 2019. Now, this is a problem because that's not actually an answer. But hopefully we can see if I just factorize out 2019, I get this, and that's 2018 times 2019. I thought that was a nice question, but I like the function questions, so sure. Question 23. This is kind of an interesting question. Now, the solid cube has length 2. If y and t are the midpoints, and so are x and v. That makes that distance 1, and then this is a right angled triangle here, length 1 and 1, which makes that distance root 2, because it's 1 squared plus 1 squared square rooted. Now the same happens down at the bottom, obviously, that length is also root 2. And now what they're doing is they're cutting through this shape. And this is hard to know without, well, if you can visualize this, then great. Sorry, I'll just adjust the mic. If you can visualize this, then amazing. But when you cut through a plane like this, what you end up doing is you end up drawing something that looks like, and this hopefully will load for me in just a second. Apologies for wasting some time here. Yeah, sorry, this should come up. Hopefully. Don't know, will it? I'd like to be able to cut this kind of thing out, but okay, there we are, perfect. Sorry, hopefully that wasn't too long. But when you cut through a shape like this, and I've got it up here, essentially if I put these in roughly the right places, I think I can get it to work. So yeah, we're going to cut through the midpoints. I think I'm going to need to shift this, probably not like that. I'm probably going to need to shift this down, or maybe put the turn less. Yeah, there we are, perfect. So if you cut through this and try and get it roughly right to be halfway, you end up seeing that you end up making a regular hexagon. If you cut through all of the midpoints, it cuts across like this. It doesn't just make a rectangle straight down, it cuts across to the other two midpoints as well to make a regular hexagon. So what you actually end up doing, I'll just get rid of this. Sorry, that whole thing was a bit weird. Is you make a regular hexagon as the face that you cut out, all with length root 2 because it's all symmetrical. And we're essentially just asking for the area of this. So okay, let's just deal with one triangle to this center. Well, the interior angle of a hexagon is 120, so that means this angle is 60, and that means actually all the angles are 60, which also means that this is equilateral, which means that length is root 2. So the area of one of these triangles is a half times root 2 times root 2 times 60, just using the half AB sine C formula. Root 2 times root 2 is 2, times a half is just 1, so that's just sine 60. Sine 60 is root 3 over 2, again, just knowing your exact values. But of course there's 1, 2, 3, 4, 5, 6 triangles to deal with, so times it by 6, and you get 3 root 3, which is the answer. Quite a tough question, especially if you're not good at visualizing that kind of thing, or if you didn't just know that that's what happened. They've asked this question a few times, so if you had done a few past papers, you might have known that that's what it looked like. Okay, question 24. I have no idea how you're supposed to know that this would work. You can just multiply x, y, and z. Trust me, you can, and it does work. I didn't type it up because it was just awful. But you can just multiply what you see together and it will work. What you're supposed to do is notice the symmetry within all of these x, y, and z's. And you're supposed to notice that if you just square z, so here's, sorry, or x, we'll do x first. If you just multiply it by itself, of course this times this, when you have a root you can just put the two things you're multiplying underneath that root. So this is just this times this. This is this times this and this times this. There's minus 2 essentially of the cross terms. And then plus, because 2 negatives, this times this underneath the root. But of course this is multiplying by itself. So underneath a root that just cancels and you get this. And this here you can multiply out to get 144. The cross terms go away because it's plus minus, and then minus 3 times 3 is 9 times 7 is 63. And that goes underneath that root, so 144 minus 63. And again, this is a copy of itself under a root, so it just cancels and just lives with itself. And it turns out to be really nice, right? This makes 81. The root 7s cancel, and you just get this. That's 9 times 2 is 18, and x squared is 6. And you do the same, exactly the same trick with y, and you do exactly the same trick with z. And then what you do is you choose to multiply together x, z, y squared, z squared to make 144, and then magically, if you just square root both sides, you get the answer is 12. If you did that without looking at the mark scheme in that way, that was really impressive of you to figure that out. I certainly didn't. I just, like an absolute madman, multiplied x, y, and z together until I got 12, which does work. It's just absolutely brutal. But anyway, yeah, great. Question 25. Got 2 circles. Importantly, the center of each circle touches the other circle, so the center must be like here, which makes the radius outline like 1. And importantly, the radius up to here, 1, and maybe down to there, 1. And now, the center of this square is going to have a length of a half across to the same point I was starting, because this length out to this length, that's the distance, that's just the radius of the circle, right, from the center to the edge of its circle, so that's 1. So I'm halving that to say this distance is 0.5. And now why am I doing that? Well, because I'm kind of interested in this length, which I'll call x. And the reason I'm interested in that length is because I think I can probably work it out. And also, if I know x, sort of half of the diagonal of the square, I can then work to getting the side length of the square. And getting the side length of the square would enable me to work out the area. Right? So if I can work out this x, I'll be good. That's my plan. Now, of course, I can do that because this angle here, well, straight up would be 90. But this goes straight up, and then you add this kind of 45 degrees to get to this corner. So 90 plus 45 gives you an angle of 135 in here. And of course, this is just a triangle I can do cosine rule on. So 1 squared equals 0.5 squared plus x squared minus 2 times 0.5 times x times cos of 135. So again, I need to know exact values here. Again, cos of 135. Well, cos of 90 is 0. The cos graph starts going down. You go another 45 degrees, so it's in the negatives. And it's negative root 2 over 2. Draw out the graph if you need to. But yeah, knowing exact values does help here. Times everything by 4, I think is probably what I did here. Oh, no, I did this. Okay, well, you get to this quadratic. Okay. And obviously I want to solve this. Now, this is not nice, but I think the formula will do. So, I mean, it's question 25, so I'm not completely above getting out heavy machinery like this. 2 squared is 4 times root 2 squared is 2, so that's going to be 8. That's going to be a plus because there's 2 negatives. You end up with this. 56 is 4 times 14, so you can take a 2 out. Then you can divide everything by 2 to get this. And I've only taken the positive here, because of course if I use the negative, it would be minus minus, and x would be negative, but I know x is positive, so I'll use the positive length here. Now, what's my plan here? Well, 2x is the entire diagonal, right? And now if I want y, like I want the side length, but I know that, well, actually, I want the area. So if I call this side length of the square y, I want y squared, that'll be the answer. Now, I know that if I have the diagonal, which is 2x, I know that y squared plus y squared is 2x squared. Which means 2y squared is 2x squared, which means divided by 2. This is the answer, remember. Y times y is the answer, it's the area. So I know 2x, and I just need to square it and divide by 2 for my answer. So I need to take this, I need to square it, which means timesing it by itself, obviously. Expand these brackets out, I guess. You get this. And then I need to tidy that up. 28 is 4 times 7, isn't it? Oh, nice. So that means root 4, root 7. Root 4 is 2, so times that by 2. And then divide everything by 4. And you get 2x squared is 4 minus root 7. And all I need to do is divide that by 2 to get my answer. So divide by that by 2 and you get the answer of A. Yeah, that was a difficult paper. That was a difficult paper. Really well done if you managed really any of the last 10. I thought they were all quite tricky.